Okay, so our next video is going to be about tectonic plates. The entire Earth is covered by the lithosphere. So remember in our last video that the lithosphere is a layer based on physical properties, and it's the outside layer that we live on. So the entire Earth is covered with lithosphere, everything. Even the oceans have lithosphere, or sometimes it's called crust, underneath of it. So I've had a lot of students in the past think that the continents, like the land that we live on, float on top of the ocean, but that is not true. The continents do not float on top of the ocean. The entire Earth is covered with lithosphere. And then on the low parts of that, where it's the thinnest, that's where the water collects, and that's where the oceans are. So the entire Earth is covered with lithosphere or crust, and some of it's just thicker, and so that's where the land sticks out, and some of it's really thin, and that's where the water collects because it's the lowest point. But the entire Earth has lithosphere or crust surrounding it, the entire thing. But this lithosphere is not perfect. It is broken up into big chunks. It's broken up into big pieces, kind of like a jigsaw puzzle. So it covers the entire Earth, but there's these big pieces that fit together to cover the surface. And these are called tectonic plates. Okay, the tectonic plates can have just an ocean on top of it, or it can have ocean and land. And it just kind of depends on the thickness. If it's a really thin area of the lithosphere or the crust, then it may just have an ocean. But if it is a tectonic plate that has a thin part and a thick part, then it's going to have ocean and land on top of it. Where there's an ocean, it's called oceanic crust. So if it's real thin, it's called oceanic crust. It is dense, so it has a higher density, and it's thin. Where there is land, it is called continental crust. So if it has a continent on it, it is called continental crust. And keep in mind, remember that a tectonic plate can have just an ocean or both. So it might have just oceanic crust, or it could have oceanic and continental crust on it. Just depends on which plate it is. The continental crust is less dense, so it has a lower density, and it's thick. So it's kind of crumbly, and it's a lot thicker because it sticks up out of the water. So the space between the plates, so if you look at a jigsaw puzzle, you know how there's that space between the two pieces? That is called a plate boundary, and we'll learn more about those in a future video. There are 7 major plates that you need to know. There are a lot of little ones too, but you don't need to worry about those as much. But the major plates are pretty much named after the area of the world that they cover. So like North American plate is where North America is. Makes sense, right? The North American plate has the continent of North America plus some of the Atlantic Ocean. The South American plate has South America on it plus another part of the Atlantic Ocean. The Eurasian plate, this is a plate that has the continent of Europe and Asia on it, and then it has some of like the Mediterranean Sea and the North Sea and kind of those oceans around Europe and Asia. The Pacific plate, so the Pacific plate is a good example of a plate that only has ocean on top of it. There's not really a lot of land. There's like Hawaii and like little islands here and there, but the vast majority of the Pacific plate is just ocean. So this has almost the entire Pacific Ocean on it. Indo-Australian, this has the continent of Australia as well as India. So it's a plate that has kind of that whole Southeast Asia, Indian Ocean, area on top of it, and the Antarctic plate. So this has Antarctica and then some of that water, the southern part of the oceans that are right around Antarctica. So there's 7 major plates that you need to know, and it's pretty easy because they just go based on the continent or the ocean that's on them. And then there's some smaller plates. So there's like the Nazca plate, which is off of the west coast of South America. And then my favorite is called Juan de Fuca. So I think it has the funniest sounding name, Juan de Fuca, F-U-C-A. And it is off the west coast of the North American plate, and it's off of like Seattle, like off of Washington. It's really little. So there's 7 plates and then a bunch of little ones, but just worry about these for now. So the tectonic plates, which are part of the lithosphere or the crust, float on top of the asthenosphere. So if you remember, the asthenosphere is the layer right below the lithosphere. So you have these plates on the top and then the asthenosphere right below it. Heat from the core creates convection currents in the asthenosphere. And we're going to talk about that in a second. So the core heats up and makes convection currents. So remember this from our thermal energy videos. Because of the asthenosphere's gooey texture, it moves, dragging the tectonic plates along with it. Okay, so I've drawn you a picture, so let's take a look at this. So here on the top is our lithosphere, because it's the top layer. We have a plate boundary here, so this is the space between two of our plates. We have two tectonic plates here, and there's one of our boundaries. And then down here is the asthenosphere, so it's the layer right below the lithosphere. So down here in the bottom, where you can't see, is the core. And that creates a lot of heat, because remember, the core is incredibly, incredibly hot. The inner and outer core is very, very, very hot. So it creates convection currents. And remember from our thermal energy transfer videos that when you have a heat source, it heats up, and because it heats up, it becomes less dense and it rises. So the material in the asthenosphere closest to the core heats up, and then it rises. And so here's our red arrow. Then when it gets further away from the heat source, it becomes more dense because it cools off and it sinks back down. So remember, this is how we get a convection current. This is the same thing that happens in a lava lamp or like a pot of boiling rice. It's the same thing. So this convection current's going this way, but maybe over here, the convection current is going this way. So the material in the asthenosphere, remember, it's hot and gooey and a little liquidy, but kind of still thick. It is going like this, and so it pulls the tectonic plates along with it. So if it's moving like this right here, it's going to pull this plate this way, and then this plate is going to move that way. So these two plates are moving apart because the convection currents are moving apart from each other. If these convection currents were moving this way, then these plates would move towards each other and something different would happen. And we'll see that in a different video. Okay? But it's really important that you understand how these convection currents work. If you don't, make sure you go back and re-watch those thermal energy transfer videos, because this is a really important concept for you to understand. Okay? So these plates are moving either apart from each other or towards, or they sometimes move past each other this way, and we'll talk all about that in another video. Okay? So pause this, go re-watch energy transfer, thermal energy transfer if you need to, and then come back. And then lastly, 245 million years ago, way before, T-Rex, like way, 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 way long ago, all of the continental crust, so all of the crust on the Earth, or the lithosphere on the Earth that was really thick, was all together. It was all in one spot. And it was joined together in a supercontinent called Pangaea. Pangaea. I don't know what the extra A is for. You don't pronounce it. Pangaea. So scientists, how they figured this out was that they used fossils found on the east coast of South America and the west coast of Africa as evidence of Pangaea. So if you ever looked on a map, like the west coast of South America fits like right in the east coast of South America fits into the west coast of Africa. So if you look at Brazil, that whole area, if you just slide it over, it looks like it fits perfect in that kind of little nook in Africa, right? And so what they did is scientists looked, and sure enough, on this side of South America, there were fossils of animals and dinosaurs and stuff identical to stuff on the west coast of Africa. But how can that be? Because if they were in their current spots, thousands of miles across an ocean, how could we have identical fossils? And so scientists believe that that's because those two areas used to be right next to each other. And so those animals could just walk back and forth because it was all one big piece of land. And then when those broke up, the fossils went along with it, and now those two continents are in two different places, even though they used to be together. The tectonic plates gradually moved to where they are today. So they separated and kind of moved apart and kind of shifted, and the continents are where they are today. But what I think is really cool is that scientists believe that in 250 million years, give or take, there will be another supercontinent. So the continents are still moving apart and towards and around each other, and that in 250 million years or so, they will be all back joined together. So when I say they gradually moved, it's like a centimeter a year, like that much, right? They're not moving very much. But when you consider 245 million years at a centimeter a year, that's a lot of space. Over a long period of time, they can really move quite a distance, even though we don't really notice it because it's moving so slowly. So plates move, convection currents, density, all kinds of crazy stuff going on. Plate tectonics.